The internet doesn't feel physical. There are no wires, no distance, no weight. But if you want to find the real internet, you have to look at the mud. 99% of all international data travels through cables on the ocean floor, barely as thick as a garden hose. And if these cables are so important, why don't we just build more of them? But it turns out the hardest part of an undersea cable isn't the ocean, it's the beach. And that's only one of the problems. The internet isn't spreading out. It's compressing into a few critical paths, and every year, those paths get more crowded and more fragile. The reason we can't just build more comes down to one thing. What happens when advanced technology meets the physical world? When people hear undersea cable, they usually imagine some massive high-tech pipe. But in reality, for most of the trip across the ocean, the cable is only about an inch thick. Inside, you have tiny strands of glass, fiber optics, about the size of a human hair. To get data from New York to London, you have to shoot lasers through those glass strands. As the light travels thousands of miles, the signal becomes weaker. To solve this problem, you need a device called a repeater, placed about every 50 miles. A repeater boosts the signal so it can travel farther without fading. Repeaters use a lot of electricity. They need this power to detect and amplify the weak light signals in the cable, restoring them so data can keep moving over long distances. So when you lay a cable across the Atlantic, you are not just laying a data line. You are also building a 3,000-mile-long power cord along the ocean floor that can carry up to 10,000 volts. This changes how the whole system works. You cannot simply drop a cable in the ocean. Instead, you are building a continuous system under the sea. A project like this can cost more than $300 million. Some projects even cost over $1 billion. That is why we do not build extra cables. You build only what you need to make a profit and not a mile more. And this is the part that surprises most people. The ocean is actually the easy part. Once you get to the coast, things get complicated. Every cable needs a landing station. This is where the cable connects to the network on land. And you can't just pick a random beach and start digging. First, the seabed has to cooperate. Experts survey the area using sonar and other mapping tools to check if it's flat enough and safe for cable burial. It needs to be flat, usually sandy, and most importantly, stable. If it's rocky, uneven, or protected, you just don't land there. There's no real workaround. You just have to look for a better option. Even if the seabed is suitable, you're not done. You still have to deal with everything happening above it. Fishing industries, shipping routes, military zones, you have to coordinate with all of them. Sometimes compensate them, sometimes redesign the route entirely. And then there's the government. In the United States, a group known as Team Telecom reviews every cable landing. Their job is simple: decide whether a cable is a national security risk, and that decision can override everything else. A few years ago, Google and Meta built a cable from Los Angeles to Hong Kong. It was almost finished, but at the last moment, the US government stepped in and blocked the Hong Kong landing. So now you have hundreds of millions of dollars of infrastructure sitting on the ocean floor, completely unused. All because of the last 50 feet of land. That's why cables don't go everywhere. They go where everything lines up: geography, permission, politics. Now you might think, fine, just go somewhere else. The world is huge. But this is where physics ruins the plan. The internet depends on speed, latency, the delay between action and response. And at global scale, distance is everything. Because light only travels so fast, the shortest route is always the most valuable. So cables get forced into narrow corridors, and once they're there, they rarely move. Take Egypt. If you want to send data from Europe to Asia, the shortest path runs through the Mediterranean, across Egypt, and into the Red Sea. A large share of that traffic passes through this one region. Dozens of cables in one place. And if something goes wrong there, the impact isn't local. It spreads across regions. So why not build a backup route? Because longer routes are slower, and slower means less valuable. So instead of spreading out, the network keeps returning to the same narrow paths over and over again. The internet doesn't fail everywhere. It fails in the same places. So let's say you ignore the cost. You get the permits. You don't care about speed. There's still one problem. How do you fix them? These cables break all the time, about 200 times every year. Most of the time, it's not sabotage, it's accidents, ship anchors, fishing nets. But sometimes, the ocean itself is enough. Underwater landslides can snap cables instantly, and occasionally, something stranger. Sharks have been caught on camera biting the cable, not attacking the internet, but reacting to signals that resemble something alive. It became enough of a problem that companies added protective layers to keep sharks from damaging the cables. Now imagine fixing one, 2 miles underwater. You can't send a diver, you need a specialized ship. There are only about 60 of them in the entire world, that's it. The global economy, trillions of dollars, depends on 60 ships, many of them decades old. These aren't just ships. They're floating factories, expensive, heavily specialized, and extremely hard to replace. Most were built during the 1990s internet boom. Then the industry stopped. For almost 20 years. Now we rely on an aging fleet to maintain everything. And building new ones, slow, expensive, risky. Even today, new ships mostly replace old ones, not expand the fleet. So we're adding more cables, but not the ability to fix them. If a cable breaks in the Atlantic, you might wait weeks for a repair ship. And the repair itself? Surprisingly low tech. A ship drags a heavy metal hook across the ocean floor until it catches the cable. You don't see it, you feel it. The tension builds. And then it's hooked. And slowly, they start pulling it up, and an engineer manually splices those glass fibers together. One by one, aligning strands thinner than a human hair. So if we build more cables, we may not be able to maintain them. We're already near the limit. There's another problem with building more cables. Once they're in the water, you can't just walk away. These aren't temporary systems. Every cable you build becomes a permanent responsibility. It has to be powered, maintained, and monitored for decades. Even if traffic drops, better routes emerge, or it stops being profitable. Because turning off a cable isn't simple. You're dealing with thousands of miles of live infrastructure sitting on the ocean floor, and removing it? Often more expensive than leaving it there. So every new cable doesn't just add capacity, it adds a long-term burden to a system that already struggles to maintain what exists. There's one more massive shift happening in who actually owns the internet. In the past, most cables were built by giant groups of telecom companies. They were basically designed to be public utilities, carrying traffic for everyone. But today, that's completely changed. Now, the biggest players in the ocean are companies like Google, Meta, Amazon, and Microsoft. These 4 companies alone now own or lease more than half of all the cable capacity on the planet. To give you an idea of the scale, Google alone has invested in over 100,000 miles of subsea fiber, which is enough to wrap around the entire Earth 4 times. But here's the part most people don't realize. These companies aren't building cables to connect the world. They're building them to connect their own infrastructure. They need their data centers and cloud regions to talk to each other instantly. For example, a company might build a massive direct link between the US West Coast and Asia just to sync its internal servers. It's a logical business move, but it doesn't necessarily make the rest of the network any safer or more redundant for the public. This means that instead of the internet spreading out and becoming more resilient, it's actually doing the opposite. We're building more and more capacity exactly where it already exists, reinforcing the same high-demand routes and the same dangerous choke points. The internet isn't actually expanding outward, it's just digging a deeper hole in the same few spots. So why not skip all of this and move data into space? On paper, satellites look like the solution, but in reality, they solve a different problem. They're great for remote access, but they can't match fiber. A single cable can carry more data than thousands of satellites, up to 250 terabits per second. To replace ocean cables, you'd need an impossible number of satellites, and then there's latency. Space is far. Sending data up and back takes longer than through fiber. There is no plan B. The internet lives in the mud, and it will for a long time. So why not just build extra cables purely for backup? Redundancy sounds simple until you realize what it actually means. You're spending hundreds of millions of dollars on infrastructure that might never be used, just sitting there, waiting for something to go wrong. And most of the time, nothing does. So from a business perspective, that capacity looks wasted, which is why companies don't build for worst-case scenarios. They build for demand, efficiency, and for return on investment. And that creates a system that works extremely well under normal conditions, but has very little margin when something breaks. The internet isn't designed to be perfectly resilient. It's designed to be just efficient enough. So why can't we just build more cables? Because the internet isn't a cloud, it's a physical system, limited by physics and shaped by politics. We like to think we've built something invisible, but really, our entire civilization rests on a few dozen cables in the dark, miles beneath the ocean. The next time you click a link, just remember that data traveled through Egypt, dodged an anchor, and crossed the ocean through a strand of glass. It's not a miracle of technology, it's a miracle of logistics, and it's far more fragile than it looks.